And in terms of the analytical toolkit more generally then, what else do we have other than the next generation sequencing that could add value to these characterization studies we're talking about?
I mean, I suppose I'm a clinician and not a lab scientist, and I have to be careful about that. And I think, a lab scientist will give you a much more detailed view because that's their sphere of practice. But
you're interesting though, because you're, I think, quite rare insofar as you're at the cutting edge of the science because you're scientifically trained with your PhD, but you also see patients all the time, and you can help bridge the two. I think it's so important because there's so many times you speak to someone, we've got this amazing new technology, it was an amazing idea, it's going to be so good.
Yeah.
And then they bring it to a clinician and they just go, that's just never going to work. Yeah. Because this is how a hospital works, and these patients, by the way, they're people, and they're just never going to do that. Do you know what I mean? So I think it's really, it would be good to hear your perspectives on the toolkit.
So the toolkit, I suppose, the sequencing is really good because it lets us know what's there, and it does that in a kind of hypothesis-free way without the biases of things like culture. Because if you try and culture a stool, for instance, to try and get bacteria out of that and find out what's there, you're always going to find things that are better at growing will come to top. So E. coli, being a good example of that, grows really easily in most environments, and so it will grow first. And in doing that, it will outcompete other bacteria for nutrition, and it will, squeeze them down, and you'll not see them as much, So that's a good reason why using stool culture or other cultures is a problem, because you're not getting a kind of pure representation of what's going on there. The culture bias creeps in and starts to change that. But culturing bacteria is still helpful and important, because then you have a bacterium in front of you. You can look at that in its own right, in terms of, okay, what do we know about this bacterium and its cell surface proteins, about how it interacts with immune cells, about what its growth criteria and conditions are. Let's sequence its genome and see what genes it expresses, and what toxins it might produce. You might think about things like antibiotic resistance, which you could obviously do in a lab setting, but you might increasingly be able to do by genome sequencing, and so that's one example of how growing bacteria can still be helpful, and it's probably a bit of a dying art in this field because everyone's rushed over towards molecular sequencing, But in addition to the approaches of sequencing bacteria, there's this whole package of things called multi-omics, which basically describes all these different technologies that can be applied to different sample sets. My colleague Professor Kostas Gerasimidis, who kind of leads up our scientific group in Glasgow, he's a great fan of short chain fatty acids as a kind of marker of what the bacteria are up to, so we do those alongside our stool samples for looking at what bacteria are there, but also what are they up to and what does that tell us about their metabolic activity. You could look at what proteins they're generating as a sort of proteomic approach, or even what proteins the host is producing in response to that.
Wow.
Or
so much.
There's an infinite number of scientific approaches you can now apply to this, but the challenge becomes actually the size of these data sets is enormous, and the data analysis required to try and integrate them and to pull that together into a single question becomes very complex. But in there lies great opportunity to try and understand disease in ways that we've not thought of yet. So if you throw a multi-omics approach at something and catch all these different huge data sets, and you also have good clinical, and this is why my part becomes important as well, and where my expertise is probably relevant, is good clinical definition of who this person is, what they have. We talked earlier about, okay, they've got Crohn's in one part but not in the other part, so that we might describe that as their phenotype.
Right.
What phenotype of Crohn's do they have? What does their blood cells and immune workup look like? What medications are they on? What the drug levels of those medications are? All of that part is as relevant as all the scientific toolkit to try and understand what's going on, not just in this person, but in this cohort of people.
Right.
And then let's throw a digital question at that. And that digital question might be, how do we tell the difference between responders and non-responders?
Based on the microbiome,
based on all of that, and see what comes out.
And is this part of the I know it's a buzzword, but the AI piece,
Yeah.
does that fit in?
Yeah, so that's why this is starting to change and starting to become very exciting. There's this new-ish concept. Probably someone in the field will say we've been talking about this for 20 years. To me,
almost certainly,
it's new. You know, this idea of machine learning. So basically, that you basically have a computer that goes through all of that and tries to look for signal, and the benefit of that really is that the computer doesn't care what your favorite bacterium is, you know, or how much effort or energy or expense you've spent on this part of the scientific process. If the signal's up here, it's going to show you that that's where the signal is, you know. Right. And so, you know, the purest scientists might say, well, you're kind of getting away from the core scientific principle of having a hypothesis and testing that hypothesis, and you're now just rolling into what does the machine tell us? But of course, the machine might point us in directions we haven't thought of yet and say, okay, the most important signal in ulcerative colitis is this one protein being synthesized up here. And if you can target that, then, you know, so we might change the paradigm of disease.
Could be the red sock and not the umbrella.
Could be the red sock.
And the machine, doesn't have the biases that I guess we do. I suppose it's programmed by us, so maybe it does. But so are you implementing the machine learning into your work now?
Yeah, we are a bit, you know, and I think that's the step that has come from, it used to be about bioinformatics, which is about transforming all those data sets into usable data that you can put into a spreadsheet or into SPSS or whatever and to do an analysis on. But as you pile on more and more data sets within this multi-omics sphere, you need to find ways of integrating those and still interrogating it. And that's where machine learning has come in, really. And that's, you know, that's probably our major use of it, is to try and integrate complex data sets and to try and answer, you know, but it's all about both the simplicity of the question that you ask and also that question is pertinent.
And the quality of the data that goes in, right? Because I suppose you need the data to be true and valid for the signal that it picks up to be true and valid as well. But
you also need true experts in all aspects of that analysis, you know, so the bioinformaticists that we've had who've helped us with our data set and these, you know, machine learning experts, many of whom are bioinformaticists, that's a really sought after specialty within the scientific community right now.
Are there trained clinicians who are now getting into this expertise as well? Is it still more of like a basic science, bioinformatics, computer science type thing?
Yeah, I don't think, I feel quite strongly about this. I don't think that's our role. And I probably very specifically think that it's almost important, like a lot of clinicians do believe that they can just be a jack of all trades because they're quite smart people and they've gone on a journey and they understand the disease. But, you know, these tools change very quickly. And I remember when I was we talked about doing my first next generation sequencing project earlier, and I remember distinctly the day that my data arrived back. You know, here I was, a kind of young registrar doing a PhD, keen on this, excited about this, £35,000 was spent on sequencing. The data came back. I excitedly downloaded it to my computer, you know, and I thought, I can't wait to see what I've got back. And what I got back was one notepad text file of 4 gigabytes of A's and C's and T's and G's and some little tags, you know? And at that moment, I transformed my understanding of what this was all about to the point that, okay, I need someone who gets this and who can turn this into something that I can understand, because I can't go there. And for a while, I entertained the idea of like, I'm going to teach myself to be that person because I want to be able to get into this, you know? But if I'd done that in 2012 or whenever that was, in 2022, it's irrelevant. The tools have all moved on. There's different iterations. There's different processes.
Moved on a lot, hasn't it?
Huge, you know. So let's specialists be specialists. You know, let's not pretend that the clinician's job is to be a bioinformaticist. It isn't. The clinician's job is to define the clinical cohort and the clinical question and to make sure that the clinical part is good, but also to be able to understand enough about these things to be conversant with these people about what it is that we need from them. You know.